pleased to announce our next speaker, M. Thompson, who will describe deformations for us. So, thanks, M.
Great, thank you. Thank you for the opportunity to speak. I guess this is maybe a vague title. So when I say deformations, I mean deformations of hyperbolic structures. Okay, so a couple of parts to this. I'm going to talk about describing hyperbolic structures and their deformations from the viewpoint of triangulations. So we'll start there. And then in the second part, we'll see a change of variables that sort of uncovers extra algebraic structure that we can use to our advantage. Okay, so hyperbolic knots are our sort of context. Everything I say will pretty much apply to any cusped hyperbolic three manifolds. But for simplicity, we're going to restrict focus to knots in S3. So we say a knot is hyperbolic when its complement can be endowed with a hyperbolic metric. Hopefully this is familiar to everyone who's been playing along with this workshop for the last couple of days. There's been a lot of talk also about Mostow-Prasad rigidity. So what that says is that there is a unique complete hyperbolic structure on a knot complement. But what people probably haven't been talking about so much so far is these incomplete structures. So it's possible to deform this complete structure and come up with new hyperbolic structures that are no longer complete, but interesting nonetheless. And so this idea of describing deformations is really describing how we can deform the complete structure and what the space of these deformations looks like. And as I said, I'm going to do that using triangulations. So we know we can triangulate knot complements. This is a convenient way to sort of break down the problem into bite-sized pieces. So we do this with an ideal triangulation, meaning that our tetrahedra don't have vertices, or you can also think of those vertices as being sort of infinitely far away. And yeah, you can chop it up and into however many tetrahedra you need, and then you have gluing information to tell you how to recover that space. So these things are kind of hard to picture. I've given you the sort of triangulation for the figure 8 knot complement, but the intuition for this is like where the vertices used to be in the tetrahedron is where your knot used to be in S3 when you glue these tetrahedra together. So here's a more interesting example. So this is the knot known as K54, and it takes 5 ideal tetrahedra to triangulate this knot complement. So I've given you this gluing information in a couple of different ways. So the visual version is these 5 tetrahedra, and I've labeled all the edges with these colored arrows. And so this sort of uniquely determines how you glue these things together. So for instance, you can see this front face here has a red edge, an orange edge, and a blue edge. And I think it glues over here to this red, orange, blue. So this is completely encoding the triangulation for this knot. And I've also shown you the Regina notation for this gluing information as well, if anyone's interested in that. I actually also intended to share my slides, but I can do that at the end maybe, if anyone wants to follow up with these triangulations. Okay, so this is the triangulation that we're going to sort of keep coming back to as a worked example throughout the talk. So the idea is to talk about the hyperbolic structures on the knot complement using this triangulation. And so we need to be able to think about the hyperbolic structures on the tetrahedra and then how they glue together. So we're going to think about our hyperbolic geometry in upper half space. So this is the upper half space model. It's, the upper half space. We endow it with the metric that sort of takes Euclidean metric and scales by 1 over the height. And sort of the effect of this is that the complex plane down below is infinitely far away. And we also talk about the point at infinity, and together these are forming the boundary at infinity. So when we want to embed an ideal tetrahedron in this space, as I said earlier, you can think of those vertices as being infinitely far away. So we send them to the boundary at infinity in this upper half space model. And so this is a picture of what that might look like. So you have 3 vertices that are on that complex plane and one that's all the way up at infinity. So it looks like there's 3 of them, but they all meet. And this is also a picture of like the standard position that I want to be able to talk about. So it's true that there's an isometry of hyperbolic 3 space that takes any tetrahedron to this standard position, where you've got one edge that's sort of between 0 and infinity, and then you put a third vertex at the point 1, and then this 4th vertex gets sent somewhere that is completely determined by the geometry of that tetrahedron. So it's some complex number on the complex plane, and we can arrange for this to have positive imaginary part. And so somehow the idea we're getting at for this talk is like parameterizing all the hyperbolic structures. And so we've got this Z variable that's somehow associated to the geometry of this individual tetrahedron. And so we can let that vary to be able to parameterize these structures. So we can notice that we can sort of move our tetrahedron into that standard position in multiple ways. So it depends which edge you're sending to that axis between 0 and infinity, where that 4th vertex ends up. And so I could say a whole lot more about these edge parameters, but for simplicity today, I'm just going to dictate that if we have a tetrahedron, we label the 4 vertices in this way, 0, 1, 2, 3. And I'm going to say that these 2 opposite edges are associated to this variable Z delta A. And then opposite edges get a B, opposite edges get a C. And so this is really, it's encoding the geometry of the tetrahedron, and we're allowing these Zs to vary in a way that will let us parameterize things. But yeah, so I guess the point of this is just you get, and also the opposite edges have the same associated variable, which is coming from nice facts about the geometry of ideal tetrahedra. But yeah, I don't want to spend too much time on this, and I probably already am. So this is how we're labeling things. As I said, I could say a lot more. So let's see. We've got, so this is giving us a way to encode the geometry of an individual tetrahedron, and now we want to place constraints on those Z variables so that when we glue these tetrahedra together to get back our knot complement, that all of this geometry is still making sense. So one thing that we need is if we want a geometric triangulation, if we want a triangulation that has a valid hyperbolic structure, then we definitely don't want any flat tetrahedra. And so these are degeneracy equations, sort of just a technical condition that means that we never get flat tetrahedra. And so yeah, we just pick them up and carry them along. They're important, but I won't say too much more. The more interesting thing here is these gluing equations. And so when we have this triangulation, so we had our 5 tetrahedra for K54, we're going to sort of rebuild that knot complement by gluing according to all the gluing information. And for the hyperbolic structure to make any sense, we definitely want these gluings to make sense. And in particular, you can ensure that that is the case by sort of zooming in on one edge, so you can sort of glue together tetrahedra around a single edge at a time and make sure they glue up around that edge properly. And if you do that for all of the edges in the triangulation, then you've made sure it is a valid gluing and the hyperbolic structure makes sense. So the way this happens is we sort of go for a walk around the tetrahedra as they glue around this edge, and we sort of pick up their edge variables. And so I've shown you what happens for this. This is from the K5-4 triangulation, just a subset of it. And so for this blue edge, we pick up these parameters. So this is Z0A is coming from the 0 tetrahedron and the edge with the label A. And then you go around, you get Z1B and so on. And you want them to equal 1 at the end. And so one way you can sort of think about this is like as when we're looking down on this as a vector, you've got like Z0 to the A is this vector here, and then we're multiplying them together. And as you go around, you want to get back to 1 at the end for it to make sense. Okay. Yeah, I guess I was maybe not clear about what this picture is. So hopefully that was not too confusing. And I'll say more explicitly now, we're sort of imagining ourselves up at infinity, looking down on the triangulation. And so we're seeing, so this is saying we're looking at tetrahedron 0, and the vertex labeled 2 is up at infinity with us, and then 0, 1, and 3 are the vertices down on the complex plane. Okay, and so the gluing information lets us sort of create this fundamental region. Just by following all the gluing information, we can glue up all of these faces, and this is a torus. It doesn't have the identifications because I'm lazy, but this is a torus, and it's corresponding to the boundary of the knot. So you've got your boundary of the knot is homeomorphic to a torus, and this is the torus that we're looking at. And so that's determined by the triangulation, and then we can just look at all of the gluing equations from this picture. So we see the blue one again, and we can do that for each of the different edges in the triangulation. And you'll notice there's 2 copies of each edge, but that's just both ends of the same edge that goes out and comes back. And so it's the same. We don't get new information. Okay. So with the gluing equation satisfied, that's giving us a legitimate hyperbolic structure, but we haven't said anything about the completeness of that structure. So the way to sort of keep track of the completeness is to think about the meridian and the longitude of the knot. So in this picture, this is the meridian and a longitude. And it turns out that the complete hyperbolic structure is exactly corresponding to when these curves pick up, like the parameters that they pick up along the way, multiply to 1. And a way to think about this is like in the universal cover, so in upper half space, we want for the complete hyperbolic structure, this sort of fundamental region to be able to completely tile hyperbolic space, and that's going to give us a complete structure, and that happens when these holonomies equal 1. And on the right here, I've shown you what happens when they don't equal 1. So if the meridian and longitude were not purely translational in this picture, then you, as you sort of glue them together, you get this spiraling behavior, and that turns out to be incomplete. So you could try and fill up hyperbolic space with this fundamental region, and you would fail. There's points that get missed, which means it's not a complete structure. But the nice thing we can do here is, instead of demanding that these things equal 1, we can instead ask that they equal variables M and L corresponding to the meridian and longitude, and that gives us the flexibility to encode the deformations. So this is sort of the crux of the describing deformations as standard. So we get this set of equations, we've got the degeneracy equations, we've got the gluing equations, and we've got the holonomy equations. So this is equaling M and L, as I said. And so these are all constraints on the tetrahedron variables that must be met for it to be a hyperbolic structure. And the L and M are allowing that flexibility for moving away from the complete structure. And so if we go through and eliminate all of the Z variables here, we end up with a polynomial in L and M. And I've cited Champanica here because he sort of connected this two variable polynomial to the A polynomial, if anyone knows anything about that. Okay, so this is sort of, most of this I should say is like work of Thurston. I put him in the top corner there for many of these slides. So this is all sort of known stuff for quite a while. And then for the next part, I want to talk about changing our perspective on this and uncovering some more structure. So one thing we can do is sort of whack all of these equations into a matrix. So we can encode everything those equations say, or at least everything the gluing in completeness equations say, in a matrix like this. So we just get a row per edge and a row for the meridian and longitude. So as an example, this was our gluing equation for the blue edge, and you just put in the number of times they appear here. So Z naught A appears once. So that's where this one comes from. So this is the incidence matrix. And then from that, you can generate the Neumann-Zagier matrix. So obviously this goes back to Neumann and Zagier. And basically you just take, for each triple of columns, you take away the C column from the A column and the C column from the B column. The reason why is obvious if I had more time to tell you, but I don't. So that's just how we do it. But the nice fact here is that this matrix has symplectic properties. So what I mean by that is there's a way to sort of extend it so that it is a symplectic matrix. So each row has a corresponding pair such that the pair is symplectically dual to each other. So the meridian and longitude, it turns out, are always dual to each other. For the edge gluing equations, you need to sort of introduce a new row into your matrix. And this is perfectly doable using some symplectic linear algebra. I've left them as stars here because I didn't go through the details. I will just note that Jessica Purcell and Dan Mathews have upcoming work where you can actually work out these rows from the triangulation as well. So that's exciting stuff. So the point is now, though, we have this matrix is now square and invertible. It's relating edge and holonomial equations to tetrahedra variables. And so this is how we're doing our change variables. So we're going to get now equations for tetrahedra in terms of variables corresponding to edges and the meridian longitude. And as it turns out, the equations that we get are all in this form. So you have L's and M's, pluses and minuses, but you always have these pairs of variables corresponding to edges. So there's 3 pairs of these things, and the sort of 6 different things gamma things you see are corresponding to the 6 edges of the tetrahedron. And this is where we notice some Ptolemy-like structure. So a Ptolemy equation is something like this, relating lengths of cyclic quadrilaterals. And yeah, there's sort of this similarity going on, 2 things multiplying in pairs. But these are somehow simpler than the equations that we had in the previous method. So in those situations for the gluing and completeness equations, arbitrarily many tetrahedra could be involved in each equation. So you could have arbitrarily many variables appearing in each equation. Whereas here we have exactly 6 edge variables plus the meridian longitude variables in each equation. Moreover, if the meridian and longitude completely avoid a tetrahedron, then there are no L's and M's either. Okay, so these are equivalent systems. So these were the equations we saw earlier, that you can eliminate Z variables to get a 2-variable polynomial. And it turns out that the same polynomial will come out of eliminating gamma variables in this system. And these are arguably nicer, I would say. Okay, and I really don't have time to say much more, but the work that is much more current is about sort of using this structure to say something about the deformation space for infinite families of knots. So Josh Howie, Dan Mathews and Jessica Purcell had the paper on this from 2020, and I've been working to extend this using the fact that this extra structure that we uncovered actually is similar to the sorts of things you see in cluster algebras. And so I was able to use cluster algebras, like results in cluster algebras, to prove a result that makes calculating this deformation space easier. But I'm over time, so I will stop there.